students, welcome back to another lecture in our course Environmental Modeling and Simulation. Today we are going to continue our discussion on 2D systems and we are going to follow up on the example that we covered in the last lecture. In the last lecture we looked at a very simple 2D linear system that we can use to model relationship between two identical entities, whether they are human beings, whether they are environmental entities or even chemical products. Okay, so in the last lecture I gave the example of two entities called one of them F and the other of them was called G, and we were looking at the rate at which the value of G and F are changing. So dG by dt and dF by dt. In general, when two entities, we are looking at how they are changing over time and we are talking about a linear system, we can write a general equation that looks like so. Right? So, we have four constants. Now, the beauty here is that we can vary these four constants A, B, C and D, G and F, to show very different characteristics of G and F, which makes this very simple model very versatile. So, in the last example for in case we wanted to show that G and F have exactly identical behavior. So, what we did was we took the constant that comes before the self variable G and the constant that comes before the other variable F, and we used the same constants for F. So, the equation for F looked something like this. So, then we knew that these are two identical entities that are interacting with each other. This is the case of identical entities. Now, let's say we are dealing with a case of completely opposite entities. How will the system look then? How can we change the constants to model exactly opposite entities? So, by opposite, what we mean is that if the self constant for a variable G is positive, then similar constant for variable F will be negative and same value. They're exact opposites of each other. So, instead of looking like this, our system dF by dt will look something like this. Now, what happens when we have case of two exact opposite entities? So, let's say we have two people in the class. We are going to continue with our more informal example of two students in a class, and we want to know if they'll become friends or they will not like each other and maybe even become enemies. Because in school these things happen, people become friends or they become enemies. As we grow adult, we realize that it's much harder to make enemies. Okay. So, what happens when there are two opposite personalities? So, in that case, let's write our characteristic equation. We know that the fixed point for this linear system is still 0, 0, so we don't need to refine it. But let's write our characteristic equation. Okay, right away we can find the values of tau, delta, and tau square minus 4 delta. So, tau here is 0, fascinating. And delta here is going to be minus a square plus b square. Tau square minus 4 delta is going to be 4a square minus b square. So, if we consult the diagram that we have looked at before, tau is 0, delta is minus a square plus b square. So, notice here tau is 0. So, we are right here on x-axis. Now, if delta is positive, minus a square plus b square is positive, which means that b square is bigger than a square. Again, the initial assumption is that a, b, c, d, or in this case a and b are positive constants, which means b is greater than a. Then what we will get is a center, because now we are dealing with this portion, of our graph. So, we are dealing with the center. Now, what happens when we are dealing with the center? Let's model it. So, if we are dealing with the center, which means our delta is positive, which means that b is bigger than a, it means our phase portrait will look something like this. This fixed point is going to be a center. So, all the trajectories are going to circle around it. So let's say our initial point is here, G naught, F naught. Cool. What's going to happen is, as time progresses, F and G values are going to move in this circular path. So let's say we are starting from the first quadrant. So basically at the beginning, F and G both have mutual admiration, they're sharing notes, they're helping each other prepare for tests, unit tests, midterm, end term exams. But over time, as time passes, they will eventually enter the second quadrant. Now in second quadrant, F still wants to be good friends with G, but G is not happy, G is angry for some reason. Remember, they're opposite personalities. So maybe F does something that G cannot tolerate and then G is angry, I'm not going to share notes with you anymore. So for quarter of the time, they will, in their journey as friends, they're going to spend in the second quadrant, where F will still be good friends with G, but G will be less than 0. G will not like F. And then eventually they'll enter the third quadrant after G not liking F, where even F will be like, I don't like you either. So we have both F and G negative. So this is what's going to happen in third quadrant. And then over time they'll move to fourth quadrant, where G will change the opinion. G is like, F is a good person. Why am I not happy with them? I'm not friends with them. But F is still unhappy. So you can see G will try to help F. And over time again they will reach back to the first quadrant again for the second time, where both F and G will be positive. They will be friends. So this is a very interesting relationships when opposite personalities get together. According to this model, we are seeing that at least half of the time that they spend in second and fourth quadrant, one of the person still wants to be a good friend, the other person is angry. So this is a very unhappy place to be in. At least for 1/4 of time, 25% of time, they are going to spend in the first quadrant, where both of them are going to be good friends with each other. And another 25% of time, they're going to spend in third quadrant when both of them don't want to be around each other. So half of the time, they'll have similar feelings towards each other. I'm going to highlight it with one color. So in the first quadrant and in the third quadrant, F and G are going to have very similar feelings. Either they're going to be friends or they don't want to look at each other. And then in the fourth quadrant, G still wants to be friends, but F is not happy. Similarly, in the second quadrant, F still wants to be friends, but G is not happy. So this is what happens according to a model when opposites come together. Okay, now let's modify the model further to look for other kinds of possibilities. So let's say we are dealing with a situation where A and C are 0. What's happening here? Not A and C, sorry, A and D are 0. What's happening here? What's happening here is that we are dealing with people, dg by dt, or we are dealing with entities whose behavior only depends upon the behavior of the person before them. Not on how they're feeling. They're emotionally not connected with themselves in case of humans. But in case of chemical entities, environmental entities, their value completely depends upon the value of the other entity. So what happens in this case? So in this case, let's write a characteristic equation. In this case, we can very quickly find out tau is 0, delta is BC, and tau square minus 4 delta is minus BC, which is less than 0. So we know that tau is 0. So again, we are on x-axis. We know that delta is negative. So we are dealing with a saddle point. Now in this particular case, if B is, coming back to the opposites, if B is less than A, we'll have a very similar scenario here. If B is less than A, then tau will be less than 0, which means instead of dealing with the center, we are dealing with the saddle point. So let's see what happens when opposites come together and we are dealing with the saddle point. So we are still talking about this system, opposites coming together. So let's talk about opposites. So in case of opposites, our characteristic equation looks like this. Now in this case, we know that delta is less than 0, which means we are dealing with a saddle Now, when we are dealing with saddle, what our typical saddle will look like. So, let's say we have F here, we have G here, and then let's say this is our first eigenvector, this is our second eigenvector. Now, depending on which eigenvector corresponds to which eigenvalue, so let's say this particular eigenvector corresponds to the positive eigenvalue, then we are going to see movement away from the fixed point in direction of this eigenvector. And if this eigenvector corresponds to a negative eigenvalue, then the movement is going to be towards the fixed point. So, in that case, our motion, our flow, our trajectories will look like so. So, now we can look at our trajectories and get an idea of how two opposites behave when we are dealing with saddle when delta is less than 0. It's also possible we have to actually calculate the value of eigenvalue and eigenvector to understand how this looks like, and it would be much easier if we knew the values of A and B. I'm going to take an example very soon, so don't worry, we are going to use actual numbers. So, it is also quite possible that we have such kind of scenario depending upon the values of A and B. And again, we can look at how, depending on initial point, the behavior of F and G is going to be. F and G are going to have different kinds of relationship with each other. Now, with saddle, something very interesting happens. We have a possibility of the F and G eventually becoming 0. So, if the initial value of F and G lies on the stable manifold. Now, stable manifold is the manifold in which the eigenvalue is negative. So, the flow is towards the fixed point. If our initial value is on the stable manifold, eventually F and G will be 0. So, basically they have no feelings for each other, they could not care, right? Same thing here. If we are dealing with a stable manifold, if the initial value is in a stable manifold, eventually these two opposite personalities F and G will have complete cold behavior towards each other. They really don't care, neither enemies nor friends. Okay, students, now let's take another example and let's see how we can modify the very simple equation that we have. So, let's say you want to talk about a kind of person who is not affected by their own feelings, but only affected by how others think about them. In that case, you can take this constant which stands before the self and make it 0. So, in this case, A would become 0. F is a similar kind of person, then D will become 0. There's some kind of people who like challenges. So, in that case, if G, in that case, what will happen is that the constant before the other variable. So, for G, the constant B will become negative, and if for F, the constant C will become negative. When F does not like G, then G will chase F, that, oh, you have to be my friend, why don't you like me? Same thing here. So, we can vary the values of A, B, C, D to get very different kinds of relationships between the entities. Alright, students, now is the time for us to explore nonlinear 2D systems. In nonlinear 2D systems, we are not dealing with relatively simpler situation where characteristic equation is very easy to find out. We are dealing with terms that are present in these models where both variables depend upon each other. So, instead of having G and F separate like they are in this case, we might have a G term multiplied here, or we might have a non-linear term here like F square, like sine F. Now, in that case, we use a slightly different approach. We have to take in from the simple mathematics that we learned in the first year in our undergraduate school, linear algebra. So, we are going to first write the Jacobian matrix. So, in case of nonlinear systems, before we find a characteristic equation, we have the additional step where we find out the Jacobian matrix. Now, before I go there, I want to talk about what kind of phase portraits to expect in a nonlinear system. In a nonlinear system, we'll again have fixed point, might have more than one fixed point. And in linear systems that we saw here, we had one fixed point, it was very easy to find out. I only give you examples where the fixed point is 0, 0. So, it made life much easy. You saw that you will have saddles, you will have stable, unstable, center, spiral. You will have a very similar range of behavior that you will see in nonlinear systems. You may also have degenerate nodes or entire line full of fixed point or entire plane of fixed point. So, same kind of fixed point behavior we can see in nonlinear systems. In nonlinear systems, okay, that part again. In nonlinear systems, the the theorem for existence of unique solutions is slightly different. So I would like to take a few minutes to talk about the existence of a unique solution theorem for nonlinear system. In a common language, we can say that if your function, your system is continuously differentiable with all the variables for a given time domain, for a given time interval minus tau to tau, when your variables are varying in a given open connected set, then you have a unique solution in that domain, in that open connected set. Now, let me explain to you how it will look like. So, a nonlinear system, we can write it like this, a general nonlinear system. It's not partial, it's like this, is equal to some function of all the variables xi ranging from 1 to n, x1, x2, so on till xn in for an n-dimensional system. And then we have df2 dt, another function, same, so on till dfn dt. Correct? Now let's say we define this whole system by one capital F. Now this has n dimensions, n variable that are dynamic variables, they're changing with time. Now this system F will have a unique solution in an open domain D, open connected set D that belongs to real number, that has to belong to real numbers for a time interval minus tau to tau, if within this domain F is continuously differentiable. So all partial derivatives of F, so del Fi by del Xi, I ranges from 1 to n. All these partial derivatives are continuous. In that case, a unique solution will exist for the system F in this domain, open connected domain D, for time interval minus tau to tau. Basically, you want continuously differentiable system in a given domain for a time range, and you want it to be continuously differentiable for all partial derivatives of f for all variables. Okay, now we can jump straight into our introduction of nonlinear systems. Remember, I told you that the step-by-step process of understanding qualitatively how the nonlinear system works is very similar to the linear system. Step 1 would be to find the fixed points. So here I am giving you the steps. In the next lecture, we will actually do an example. Step 2 would be find the Jacobian matrix. Now, how does the Jacobian matrix looks like? So, Jacobian matrix J will look like so for the system F, yeah, will look like so. Partial derivative of the first F1 variable here, so on till, yeah, and then similarly for second, this is not a variable, this is a function, sorry, so on till del fn, this is x1, sorry, this is also x1. So this is your Jacobian matrix. You're going to find it. Don't worry, in this course we'll deal with only 2D systems. We will have a 3D system that we'll discuss and we'll convert it into 2D. So you'll not be dealing with very big Jacobian matrices. The third step is to find out your characteristic equation at the fixed points. We are interested in how the behavior of our trajectories is around the fixed points, right, in nonlinear system. So we want to find out the characteristic equation at the fixed point. Very easy to do. Put the value of the fixed point in your Jacobian matrix for each fixed point and then you will get the characteristic equation. Then the fourth step is very simple. You can either directly go find tau, find delta, tau square minus 4 delta, and then look at your graph and understand how the trajectories will behave around the fixed point, especially if you're dealing with a saddle or you're dealing with a spiral. Very important to find out eigenvalues in vector. So the next step would be find out the eigenvalues, how many ever there are, and find out the corresponding eigenvectors, and then you can actually do the next step, the final step, which is draw the phase portrait. As I shared in an earlier example, just drawing the face portrait is not important. You need to look at the face portrait and understand what information it is giving to you. In fact, towards the later lectures, I'm going to spend a lot of time trying to understand the face portrait, trying to interpret it, trying to interpret our model, because it is the interpretation stage that will help us understand whether our model is doing a good job predicting what we are seeing in nature or what to expect in nature, and if not, then how can we change a constants or a variable or the model overall to improve or to write better models. Alright students, this is all for today's lecture here. In the next lecture, we are going to start taking examples of nonlinear 2D systems, and we are going to start with a very famous model called Lotka-Volterra model for competition. And then I'm going to teach you how to modify this very simple model. It's a brilliant model actually, simple and brilliant model, to model other kinds of relationships in environment such as predator-prey relationship, cooperation. Again, as we saw in the linear model, just by varying the constants, you can vary the relationships. Same thing happens here in the Lotka-Volterra model of competition. All right, students, see you in the next lecture. Thank you.